forced convection apparatus. In the previous session, in the previous class, we conducted free convection experiment. We find out a heat transfer coefficient value in the case of free convection. So as here, we are going to find out the heat transfer coefficient. In a forced convection, the fluid is flow through pipe. So here the aim is to determine the heat transfer coefficient in a forced convection flow through a pipe, fluid flow through a pipe. Okay. To conduct this experiment, we are going to see the specification. First thing is specification. The specification, they are going to mention diameter of the RFI is 0.02 meter, length of the pipe, okay, there is a test section length, okay, 0.5 meter, diameter of the pipe is 0.032 meter, coefficient of discharge 0.64, there is no unit. So dimmer start is a range of 260 volt and 2 ampere, voltmeter the maximum is 300 volt, diameter is maximum 2 ampere, number of thermocouples consideration is 7 thermocouples. Okay. If you come to that setup, as in this setup we are going to consider a horizontal pipe. Okay. So as inside of this pipe the fluid is flowing. If you come near, you can observe. Okay, this is the pipe. Okay, this is a test pipe. Okay, inside of this pipe the fluid is flowing. As here we are going to consider forced convection. We are going to consider the external device, external agency to get forced air over that heated surface area. That is what, as here we are going to consider blower. Okay, from this blower we are going to get forced air. That forced air is circulate inside of this pipe, inside of this test pipe. This is a test section, right? So if we come to that control panel, as in this control panel, we can observe this. This is the power switch. Okay, this is a blower switch. This is a dimmer start voltage controller. This is a voltmeter. This is a ammeter. This is a temperature indicator. We are operating this temperature knob. We can observe the temperatures. This is a manometer, YouTube manometer. We can note down the readings H1 and H2 from this YouTube manometer. Okay. So as here we can observe this is a blower. From this blower we are going to get the forced air. Okay. This is a length of the pipe consideration, horizontal pipe, as we are going to consider. For this pipe we are going to consider the heating coil. Okay, therefore the tube is heated, as air also heated, right? When the fluid circulate over inside of the pipe, the air is heated, right? To measure the surface temperature of the pipe, we are going to consider around 5 thermocouples. Okay, these are all the thermocouple wires. So around 5 thermocouples we are going to place over the surface of the pipe. Okay, to indicate the surface temperatures. The fluid enters before the test pipe, we are going to consider 1 thermocouple. After test pipe, we are going to consider 1 more thermocouple. These two things, it says that this is, we can consider as a T1 for our reference. The fluid entering temperature, this is we are going to say as a fluid exit temperature. Okay. The remaining these temperatures we are going to say as a surface temperature of the pipe. Okay. Initially we are going to switch on the mains. After switch on this, we are going to set the voltage. We are operating this voltage controller. We are going to set the voltage. We already set 60 volt. Based on the voltage, it shows the current reading. As set the voltage, the heat is supplied to this pipe. Okay. To avoid the heat interaction to that surrounding, we are going to provide the insulation. Okay, we are going to place cotton thread to avoid the heat interaction to that surrounding. So next thing is, we are going to switch on the blower. Okay, before switch on the blower, you just adjust the valve. Okay, so you just consider different trials. For first trials, you just consider as a fully open. Next is partially open, 50% open, 25% open. Like that, we can consider the different trials. Okay, different set of trials we can consider. For first trial, you just consider this valve is fully open. Okay, so next is you switch on the blower. Okay, when you switch on the blower, from the blower we will get the forced air, as forced air is circulated inside of the pipe. Okay. So next is we are going to note down the temperatures. When the temperature reaches to steady state, okay, we are going to observe the temperature as here T1 and T7, which indicates what? The fluid entering temperature, fluid exit temperature. T2 to T6, it represents the surface temperature. Okay. So you are going to wait for to reach the steady state. When the temperature reaches to steady state, means temperature does not vary with respect to time. During that time, you are going to note down the temperatures. T1, that is the fluid entering temperature. T2, that is surface temperature. T3, surface temperature. T4, surface temperature. As in the different position. Okay, at uniform distance, we are going to place the thermocouples. We are going to measure surface temperature. T4, T5, T6, and T7. T7, it says what? One second. T7, it says fluid exit temperature. The fluid exit temperature is more than the fluid entering temperature, because the fluid catches the heat from the tube, the heated surface. Therefore, at exit point, we will get the maximum temperature. As we can observe, the T7 is 46. If you observe T1, what is the T1? 41. Compared to T7, T1 is less, right? Because of what? Heat carries from the heated surface area, right? From the tube. After note down the voltage, current and temperatures, you are going to note down the H1 and H2 value. Okay, you just observe the left limb and right limb. You are going to note down the H1 and H2 value to find out the velocity of the air. From that velocity of air, we can find out the Reynolds number. From the Reynolds number, we can decide the type of flow. Based on the consideration of Nusselt equation, we can find out the heat transfer coefficient value. The H value, that is a theoretical value, and experimental value, we can find out. This is what observation table. You just note down the voltage. Based on the voltage, as we set that voltage around 60 volt, based on the voltage it shows current reading, right? Based on this, we will get the amount of heat supplied. After set the voltage, you are going to wait for to reach the steady state. Consider forced air. Okay, when you switch on the blower, you will get the forced air. The forced air is circulated over the inside of the pipe, right? After that, you just note down the temperatures, the surface temperature, and you are going to note down the fluid entering temperature, that is a T1, and fluid exit temperature, T7. Okay. So from the surface temperature, we are going to find out the average surface temperature, and you are going to note down the manometer readings to find out the velocity of air. By knowing all these values, we can find out the theoretical heat transfer coefficient and experimental heat transfer coefficient. So next is calculation procedure. So this is some important formulas to find out the heat transfer coefficient value, that is experimental value and theoretical value. Okay. So to find out the heat transfer coefficient experimentally, we are going to use that convective law equation, convective cooling law equation, Q is equal to HA delta T. By consideration of this equation, we can find out the H experimental value. As we find out surface temperature, okay, as we know that surface temperatures, we can take average. Okay, from that we can get that fluid temperature. We are going to take the average, the fluid entering and fluid exit divided by 2. From this, we will get the difference in temperature, and we are going to find out the surface area of the tube or pipe, right? We are going to consider that formula pi dl, or we can consider 2 pi rl. As we know that diameter, you know, the length, we can easily find out the area. As we can find out amount of heat supplied, from this we can find out the H experimental value. If we come to that theoretical, we are going to find out the film temperature. After find out the film temperature, we are going to note down the properties and values for particular temperature by using the data handbook. From your data handbook, you can find out the properties of the fluid, that is what, air, for particular temperature, we are going to note down the density, kinematic viscosity, Prandtl number, and thermal conductivity value. After knowing these values, we are going to consider velocity of air, as we already find out, as we already note down that the manometer reading, right? By consideration of this equation, we are going to find out the velocity of air. As we find out the velocity of air, we can find out the Reynolds number, right? As we know that Reynolds number is the ratio of inertial force divided by viscous force. We are going to consider mathematical expression rho Vd by mu or Vd by nu, right? By consideration of these, we are going to find out the Reynolds number. As we know that one generalized equation, when the fluid is flowing inside of that pipe, horizontal pipe, we are going to consider this Nusselt expression. Nusselt is equal to 0.023 Reynolds to the power of 0.8 and Prandtl to the power of 0.4. As we find out Reynolds value, we know that Prandtl number from the data handbook. By finding out Nusselt value, we are going to consider Nusselt expression, right? Nusselt expression is what? HD by K. When the fluid is flows over the plate, we are going to consider HL by K. When the fluid is flowing inside of the pipe, we are going to consider HD by K. By consideration of this Nusselt equation, we can find out the theoretical heat transfer coefficient value. Okay. For your reference, I will consider one trial. Okay. So as we set the voltage 90 volt, we got that current reading 0.89. From this, we are going to consider the amount of heat supplied to that pipe. Okay. So next is once the temperature reaches steady state, we are going to get this surface temperature 60, 70, 72, 71, 64. So somewhat the temperatures are uniform, right? We are going to take that average, the fluid entering temperature, fluid exit temperature, and we are going to note down the manometer readings. That is the left limb and right limb. We are going to note down. Okay, from these values, we are going to find the velocity of air, right? So, and we are going to find the H experimental value by considering the result Newton convective equation. We are going to find out the H experimental value. We got around 62 watt per meter square degree Celsius. The unit is watt per meter square degree Celsius for heat transfer coefficient, right? And we are going to consider the film temperature to find out the theoretical heat transfer coefficient by consideration of 42 degree Celsius. For particular this temperature, we are going to note the properties of air from your data handbook. Next, you are going to find out the velocity of air. We are going to find out the Reynolds number. Based on the Reynolds number ranges, we are going to consider Nusselt equation. From this Nusselt equation, we are going to find out the theoretical value, heat transfer coefficient value.